All right, so I was going to show you this. So we're talking about the hydrogen atom and what these little electrons do. So here is the Niels Bohr model of the hydrogen atom. I have a lab for y'all to do that actually looks like this. So if you look on the screen here are all the different energy levels, and right now it's at n equals 1, so it's flying around in that very first one. All right, now what we're going to do is we're going to turn this gun on, and we're going to be firing different subatomic particles at it. And once you watch this little blue thing, as we fire stuff at it, it's going to get hit by stuff, and see how it suddenly jumps. It makes these jumps. If you watch that little blue dot, it makes these random jumps. And so all these little random jumps, this is something that Einstein hated, because you couldn't predict where that little sucker was going to jump, how far, how long it would hang out. He didn't like it. But this is the essence of quantum. And when you watch that little blue dot, when it jumps up into a higher energy, right, and then when it jumps back down, it actually gives off, and you can see these, boom, see it go? So it gives off little photons when it jumps back down. It gives off photons of light. And depending on how big the jump is, right, you get different wavelengths, so you get different wavelengths of light. And this is what we're talking about. Now, the thing I wanted to talk to you about is, why is it that when this thing jumps up and then jumps back down, it gives off a little photon, right? Why do all these energies have negative values, right? And so the answer to that, as I was saying, is it's like being in a hole. So on the first energy level, it's like you're at the bottom of this hole and you have to jump out, right? Now let's say, it takes you a certain amount of energy to jump out of this hole, right? Let's say it takes you 1,000 joules. If you have 999 joules and you try to jump out of the hole, you won't make it. You have to have a discrete certain amount of energy to make it out of the hole, right? So to get from the first to the second, you have to have a certain amount of energy to get out of that hole from first to second, right? And as you go, these numbers get smaller and smaller until you get to a certain point where they go from negative to positive. What does that mean? Well, at some point you can actually break electrons off. They'll go flying off, right? So they'll actually have positive energies, right? Which means that when you get to 0, that's when they get out of the hole. And if they have any energy left over, that means they actually have kinetic, and they go flying off, and you can figure out how much kinetic that they have, right? Because they'll go flying away. So you have to hit these guys with a certain amount of energy, or else they won't make those jumps. And the more that you hit them with, the bigger the jump will be. And then when they come back down, they'll let off a little photon, and each of those jumps will have different photons of different colors. Okay. But this is really the math that you need right here. And I've got some practice problems in the module that you guys can do to try to, figure these out, right? We'll try one here in a second. All right, as an example problem, what is the delta E to go from the first to the second for hydrogen, right? Well, if the first is negative 13.6, and to get to the second, it's negative 3.4. Then what is that change, right? What would be the total change to go from here to here? Okay, that would be 10.2. Okay. Negative 10.2 EV, is that right? 13.6, 13.11. Yep. So this is the change to go from first to second, is that amount, right? So the question is, if we have an electron to go from the first to the second, and then it drops back down, it gives off a little photon. What is the wavelength of that photon going to be, right? Well, we can use that equation from my first video, 1240 over lambda. We can use that to figure out what our wavelength is, right? So essentially, we just do 1240 divided by 10.2, because that's the change from the first to the second, and that would be your wavelength. And that's an example of how that works. All right, guys, so we got to talk about last couple things. Something called the photoelectric effect. This is something that Albert Einstein figured out, and he won a Nobel Prize for. And this is from the notes. So this is all in the notes, you know. I'm just doing what I would have done in class, but this is all in the notes, guys. So as far as photoelectric effect goes, right, you can actually, if you hit a metal with energetic enough light, you can actually get some of the valence electrons to come flying off of that metal, which is pretty cool. Okay, and we can use this certain ways. Here's the electron volt I've been talking about. So there's how you get that. This is all in the notes. This is in Canvas. But anyway, the photoelectric effect is when light strikes something, if it's energetic enough, it can actually give off these electrons, and you can free them from the surface of the metal. They're going to be the valence ones, and we can do stuff with those electrons, right? So this is all stuff that we've talked about so far. There's Planck's constant. You got to know a bit about light. Make sure you review all this. So there needs to be a certain amount of energy to this light. I want to show you this. This is a lab that y'all are going to fiddle with when you're futzing around with Canvas. So what I'm going to do is I'm going to turn on this lamp. This is called a photovoltaic cell, right? I'm going to turn this lamp on with 100% intense light. And you see that we don't get any electrons coming off, even though we're at 100%, because our wavelength is too low. So this light is not energetic enough. But as I go from low energy light, as I go to higher, we're going to start to see some electrons get pulled off. And as we get more and more energetic, more electrons will get pulled off. And more and more and more. And then you're going to get a current. If we go all the way to UV, oh my gosh, you get so many yanked off of there. Right? Pretty cool. So, this frequency at which we can get electrons to come flying off is called the threshold frequency. Right? And when you pull these things off, the term for that is ionization. It's a hard word for me to say. So you'll see graphs that look like this, right? That's called the threshold frequency, where you get what's called ionization. It's got to be at that certain frequency, or else you won't get electrons to come flying off. And so that's important, called the threshold frequency. And every metal has a different one. Okay. Now, there's something called the work function, and here's a definition of the work function. Okay, we're trying to pull these things off of there to create a current, right? So the whole idea here is that these electrons that get yanked off are going to make a current, and so we use this in things called photocells, right? Work function is the least amount of energy that can be supplied to get these little guys to come flying off of that metal. Okay. Now, once they come flying off, they're going to have a certain amount of energy, and that'll be kinetic, right? Well, I'm just showing you slides, but this is all in the notes here, and so you can go back and review this, okay? And this is all the stuff put together right there in one slide. I would have shown this in class, okay? So there's your work function. It's this weird looking symbol right there. HF is the energy of the photon. K is the kinetic. Okay, So there it is, all in one graph. I'm showing you the graph there. Okay, and of course we can use this photovoltaic cells, like solar cells. This is a thing that we use to generate electricity, right? It's pretty cool. Okay, so anyway, here's my last slide. These are all the different things that you kind of need to know as far as this photoelectric effect. Like I said, you're going to be doing that lab as part of the Canvas module. So there you go. So all these little electrons can bridge this gap. We get a current. We can use that to generate stuff, and it's pretty cool. They have kinetic energy because they're moving. All right, let me see if I can make myself bigger. Now, because they're moving, they also have momentum. So I wanted to show you this because you're going to need this, if nothing else, for Quest. We can start by this equation, the most famous equation, I think, in all of science. And so I'm going to come up with an equation for the momentum of a photon, right? E equals mc squared. You can think of as E equals mc times c. That would be mc squared. E, if you recall from my last video, E equals hf, Planck's constant times frequency. What's m times c? C is a velocity. So mc is really mv, which is momentum. So mc is really p. So this is momentum times c. Now over here, if you look at my last video, F is really C over lambda. And you have to rewatch that last video. Okay? But frequency is equal to C over lambda. That's a thing. And C's cancel. So now you got H over lambda equals P. And this is the equation for the momentum of a photon. And if we get, we get them to move, we get them to do things, then we can have a voltage, and they have momentum, which is pretty cool. So that's a thing, and you're going to see this used, if nothing else, on our end of year quest.